So, hello everyone, my name is Cyprien Gottstein. I am a PhD student. I work at Orange, which is France's biggest ISP. And this paper has been written by me and the help of Philippe Repin-Parvedi, Michel Irfin, Thomas Hassan, and Thierry Coupaille. They're not present today, so I will do the whole presentation. The title of the paper is Inverse Spacefilling Partitioning applied to wide area graph. So we'll go in 5 steps. First, with a little introduction about what graph partitioning is. Then I'll give you some context and how a solution works. Then we move on with the additional metrics, then the results, and finish with a little conclusion. So what is graph partitioning? Graph partitioning is defined as the following thing. You have a graph and you want to cut it into multiple blocks, pieces, or simply put partitions. And at the end, you want to have an evenly balanced partition load and you want to minimize the number of edge cuts. Edge cuts are edges for which both ends are in separated partition. This is important because each partition will be assigned to a machine, meaning that when you want to traverse the edge, if the edge is non-cut or local, if you prefer, you will be able to traverse this edge with a disk lookup or memory lookup. If it is cut, then it means you have to go to another partition, then another machine, meaning that you have to perform a network lookup, which is obviously way slower. And since edge traversal operations are very frequently used in anything related to graph, you want to avoid that, of course. This has been declared and proved as an NPR problem, and this is why I'm here. So this research has been operated on the Orange Thinking project, which is an IoT platform, so Internet of Things, IoT. This can be described as a registry for connected and non-connected objects, with connected objects such as sensors, Wi-Fi device, meteor station, smart locks, and other things, or non-connected objects like building, road, water network, bus line, or even trees if you need to, as long as you have the web definition, the web semantic definition, for those who know RDF, as long as you have the appropriate definition, we can store anything into Thingin, and everything there is stored in a giant graph. Most of the nodes are enriched with geospatial data and form a topology. Our problem is to make Thingin scale, which implies a distributed system and implies to partition and distribute the graph of Thingin. There are different types of graphs. There are regular graphs, for example, lattice, grid, and meshes. You have an example of a mesh on the top right of the slide. And irregular graphs, such as random graphs with no rules at all regarding their construction, mesh in the irregular form, spatial graph. I'm thinking of infrastructure network like power grids, roads, trains, but also natural structure like rivers, and scale-free graph, which embed the social graph, Facebook, Twitter, you name it. Each of them have their own set of properties, be it connectivity distribution, clustering, is there communities or not, what is the diameter of the graph, and in the case of presence of geometry, what is the node density distribution and edge density distribution. Unfortunately, as of today, there is no appropriate definition for the graph of Thingin. So instead, we came up with our own definition, which we named the wide area graphs, so WAG. WAG can be seen as large-scale IoT graphs, and they are a subfamily to us of geometric graphs, meaning that each of their nodes will be associated to a position within a given Euclidean space. They need to be large scale with millions or even billions of nodes and edges, cover a large area, a large space, so covering a country to a continent or even the whole Earth, and they should be composed with a layer-like structure. It is important to understand that IoT is a kind of a buzzword, and just like big data, where you can put a lot of things into it and there's no real logic behind it, IoT is maybe also a very different thing altogether. You have the smart building, smart cities, smart home, and other services which are developing. And in order to have a truly large, unique graph which will cover a large space, large area, you need to have several layers, and the low layers are graph with low density, but able to cover a very large space. So that's where the power grids and word networks comes in. And then as you move on in the layers, you will have graphs which will cover a smaller area, but with much more density, so more nodes in the same point. And all of them are bound and intertwined together, leading to a giant topology. So that's what we envisioned for WAG. Regarding their properties, we believe that if WAG truly exists, as it is only the beginning, we have yet to see we have yet to see them in a real world dataset. We see them as highly polarized version of measures. So they would have higher node density variation with desert, no nodes at all, and metropolis for extreme density, and higher edge Euclidean distance in average, leading to overall higher connectivity and a lower graph diameter. Graph partitioning now is a very rich domain, which has seen many strategies, method approach, and it is currently divided into two big families with offline and online. In offline, you are required to store the whole graph in memory in order to make a global decision for your partitioning. This obviously doesn't scale very well as graphs are becoming truly gigantic. So this is where the online family comes in, where you're not required to store the whole graph in memory anymore, but you sacrifice the global decision making to local decision making. Our work is based on ISP, so in the space filling curve partitioning, SFC space filling curve. And we mainly compare ourselves against FENNEL, which is the most, today, I think, the most standard approach of graph streaming strategies. Graph streaming partitioning strategy, come on. And an important note is that ISP is based on geometry to partition a graph. And geometry itself can be very expensive if we use it without precaution. So we do use a heuristic in ISP, and it is the use of the space filling curve. Before explaining to you what ISP is, just a little step through FENNEL. So it is based on streaming, and when you do so, every node of the graph are streamed exactly once. The order you use to stream those nodes is defined either by random, DFS, or BFS. DFS, depth first search, and BFS, breadth first search. In FENNEL, to assign a node to a partition, you will process a score with this node and each different partition. And the score is a mix between the number of neighbors of this node you can find in the current partition, and also the marginal cost of adding this particular node into this partition. The number of neighbors is simply to say that if you have a high number of edges, a high number of nodes, neighbors of the given node within the same partition, you will naturally limit the number of edge cuts. So it is how they build the score. And once you have found the highest score, you just assign a node to the given partition. FENNEL is very powerful, and also it is configurable, as you may relax the load balance constraint to have optimized edge cuts. The load balance constraint is very important because if you don't have any, the best solution to graph partitioning is actually to put every node into a single partition, and you didn't really answer the question here. So you had to preserve a kind of balance. Now, space filling curve. Space filling curve are mapping based on fractal to translate a multi-dimensional space to a single dimension line or curve. Space filling curves are cheap to process, so this is why we use them, and are used in Node because of their ability to preserve spatial proximity from multiple dimension to the single dimension. And the way they do so is a matter of ordering of how the curve will actually travel through the space to map the the plane, the multidimensional plane. And as you can see, when I give you two examples here with the z curve and the Hilbert curve, when you move from 0, 1 to 1, 0 in the z curve, both coordinates are not adjacent. If you look at Hilbert curve now, when you move to 0, 1 from 1, 0, here it is adjacent. As a matter of fact, Hilbert curve has been proved as the best curve to use when it comes to spatial proximity preservation. And from now on, as soon as I will mention a space filling curve, I will imply the Hilbert curve, as it is what we use through our experiments. Now, ISP. ISP was proposed in 1994 by Pilkington and Baden, and their goal was to partition mesh graphs through geometry using space filling curve. Our proposition is to extend ISP context to wide area graph. WAGs are essentially a harder version of meshes graph with a node density variation tougher to handle, and also a tougher connectivity, as in mesh graph, the connectivity is planar, leading to low connectivity degree and a low edge Euclidean distance. Whereas in a WAG, connectivity is not planar, meaning that you have a higher connectivity degree potential and also low to medium edge Euclidean distance. How does it work? It is also based on a graph streaming partitioning strategy. I may not have mentioned that before, but when ISP was created in 1994, streaming strategies did not exist yet. And ISP is not a streaming strategy by default, but if we look at its current requirement and the way we apply it, in fact, in 2020, it is a streaming strategy. So the base is a streaming strategy, but the order used to stream the nodes is actually defined by the space filling curve. And you have a set of partitions, each initialized with a capacity large enough so that you can store the whole graph once all the partitions are filled. And you will fill them sequentially in a greedy manner. So you take the first one, you put nodes inside it, and once it has reached max capacity, you move on to the other one. Upon completion, each partition will cover a continuous interval in the 1D curve. And thanks to the space filling curve mapping, continuous unidimensional curve interval actually maps to a continuous area in the multidimensional space. It is what is shown on the right. So you have, you won't see my mouse, it's fine. On the bottom, you have in bright purple, dark purple, you have the continuous interval. And if you look at the multidimensional space here in 2 dimensions, it will map to a continuous area. So nodes closed in multidimensional space are also closed in the unidimensional curve. And this leads to nodes closed in multidimensional space end up stored together within the same partition. If you add others, you can see that they all are plugged to each other as they follow the order defined by the curve. And when you add every partition, you will cover the whole space of your graph. We added metrics, so this is not coming from ISP original work, it is our own. We added metrics to better understand and pre-evaluate ISP performances. And a fun fact with ISP, fun and a bit strange also, is that within ISP, we do not look at the fact we are partitioning a graph. We are only interested in nodes and their position. We do not look at the edge factor at all. And EDTPS, so edge distance to partition size, is there to help us estimate in advance how well ISP will perform by looking precisely at how edges are formed, what is their properties, and how well will our results be. The CDTPC is set density to partition capacity. We could have had the time to speak about it, but I plan my presentation to be about around 25 minutes, so I'll skip it. Sorry for that. The idea behind EDTPS is very simple thinking. We take all of the edges of the graph and we process the average edge Euclidean distance of the edges. So the edge distance is simply you have 2 points in an Euclidean space. Those points are in fact nodes linked with a relationship, an edge, and you just measure the distance separating the two. And we compare that against the partition average surface converted into a square. And here's the following. If in average, any edges of the graph is wider than the surface converted into a square of the partition, then it means that at least one of the edges, one of the ends of these edges will end up outside of the current square, meaning it will end up in an other square. So you have, because you have two squares, you have two partitions, and thus the edge is cut. So on contrary, if all of the edges are very close, are very tiny compared to the surface of the partition, most of the edges should be able to fit within a single partition and thus should not be cut. So a high EDTPS ratio should imply a high number of edge cuts, and a low ratio of EDTPS should imply a low number of edge cuts. Looking to our results now, and we wanted to prove multiple things. First, we built metrics, and we want to check that EDTPS and CDTPC are truly accurate. So as EDTPS rise, we expect the edge cuts to also to do the same. As CDTPC rises, load imbalance trouble should start to appear. CDTPC is there to identify potential risk trouble, but it's not because there is a risk that you will see a problem with it. So we'll talk about it right after. And we wanted to show that ISP can scale and handle big graphs and find an inflection point for which ISP becomes worse than its concurrent. This is important to us as we believe that in graph partitioning, there isn't enough tool to properly help people choosing between several graph partitioning strategies for their graph. And this is to give hints to potential user as to when to use or not use our strategy. And this should be purely based on edge Euclidean distance, as we believe it is the ultimate factor regarding ISP edge cuts performances. Now, I gave you the definition of WAGs because there is no existing yet, so we couldn't find any appropriate datasets for our experiments, and there was no generator able to suit our needs, so we had to build our own. And in a nutshell, our generator create geometric graphs within a user-given 2D bounding box. So we use two boxes for our experiments, one which is roughly the size of France and one roughly the size of Europe without Russia. And it produces graph with varying node density, thus a varying CDTPC, and varying edge distance, thus a varying EDTPS to again have interesting value to analyze, and hopefully also edge variation. It scaled well enough to produce large-scale graphs, so the default graph size we used for our experiment was 50 million nodes and 150 million edges. This is a subset of the distance categories we use in our test. So it goes from tiny with a distance lower than which average to 1 kilometers to huge with 400 kilometers. The tiny category has been designed to approach as much as possible the properties of the graph of thinking with an EDTPS lower than 1%. And the huge was to reach the 100% of EDTPS, so to have a category where we expect to have a very large number of edge cuts. Here is the density categories. Each column corresponds to a density strength, and each row value is how much of that type of density will I use to construct my whole density distribution for a graph I'm generating. So if you look at the low category, it needs to be read that way. It is composed by 1,000 units of density 0, meaning that approximately 45% of the surface of the generated graph will actually be empty with no nodes So it will be the equivalent of ocean and deserts. 1,000 units will be at density 0.5, so 45% will correspond to rural area if we make an analogy with how human population density works across the Earth, 9% to urban area, and 1% to large city. The 50 column and 500 column are used for higher density level, representing very large city and metropolis. Again, the low category was designed to approach thinking properties, and the high category was to provoke cases where we have some load imbalance trouble and see how ISP survives through that, if it's problematic or not. Now we compare the results of ISP against FENNEL. We also did the same against LDG, which is another streaming-based graph partitioning strategy, but the results are either similar or worse than FENNEL, so I didn't show you there. There are several things to see here. First is that we have our inflection point where indeed it becomes better to use FENNEL rather than ISP with the huge category, as the number of edge cuts reaches more than 86%. And we have cases where the edge distance is extremely low with a very small EDTPS. So I'm looking at Singin and Tiny, where it is much more profitable to use ISP as we have less than 1% of edge cuts, which was the results we expected, so we're happy on that. And on the last note, if you look at the results of FENNEL, you may see that it is extremely stable. The problem lies not within our FENNEL implementation. It is more about how our generator proceeds to generate graph. The connectivity in the graph we generate is always kind of the same property-wise. So it will always have the same kind of distribution. And the way FENNEL works to partition a graph is heavily reliant on the connectivity of the graph. And therefore, because the connectivity is approximately all the same in the graph we generate, except for Tiny, the results of FENNEL are equivalent on the long run. Moving on, we wanted to check and prove that EDTPS is accurate, and it is, as you have a comparison here of the EDTPS curve and the edge cuts curve. There is only one for which it doesn't work, which is the huge category, but it's because there is a staining effect on the edge cuts, as you may not have more than 100% of your edges of the edges of your graph which are cut. It's mechanically not possible to go above 100%. It was a bit rougher for CDTPC, as again we identify a risk, and there may be a risk, but there may not be trouble whatsoever. But the good thing is that when the CDTPC is low enough, we could see that there is no load imbalance trouble induced. So CDTPC is considered as accurate. So to conclude, yes, so we just showed that EDPS and CDPC are accurate. We showed that ISP is not suited to partition every kind of graph, which is perfectly fine. With the right context, so with a small EDTPS, it outperforms concurrent strategies, and within the wrong context, with high EDTPS and long edges, it will perform very poorly. This means that if you want, for example, partition a scale-free graph such as Facebook, where all of the edges are very long, ISP is not suited for and will handle poor results to you. And the last good thing, ISP can scale. So what is our next step now? I just showed you before the state of a very simplified view of graph partitioning research domain. And here's the same, but this time filtered with which one are oriented to be, which one are to be used in an analytic context and which one in a database context. And as you can see, pretty much nothing is done toward graph partitioning in database engine. If you look today at state-of-the-art graph database. In fact, they will use the very same strategies used in SQL or NoSQL system. I'm thinking of Neo4j, TigerGraph, OrionDB, um, ArongoDB. They all use the very same thing, which is hash partitioning and range partitioning. And we believe that, unlike concurrent strategies, ISP could be adapted to work in a database context. So that's where we are going on. I thank you for your attention, and if you have questions, I'm at your disposition. Bye.